maybe you don't want to feel like your brain is, well, doing backflips.
Yeah, it can get pretty complicated pretty quickly.
Exactly. And that's why you're here with us on the deep dive. Because today we're tackling something that sounds, well, a bit out there. Spin.
It's one of those words you hear in science, and it can kind of make you go, huh.
But trust me, this isn't about like electrons actually spinning around like tiny planets or anything. It's way weirder and way cooler than that.
It really is.
It's a fundamental concept, this spin.
Yeah.
And it's kind of behind everything. From like the tech you use every single day to, how we understand the universe.
It really is everywhere when you start to look for it.
I'm excited to dive into this. And we've got an expert here to help us unpack it all. Welcome to the deep dive.
Thanks for having me. It's great to be here.
So, spin. I think a good place for us to start, for everyone listening, is by clearing up what we're actually talking about when we say spin in, the quantum world.
Absolutely. I think a lot of people, when they hear spin, they immediately picture something physically rotating, right? Like a top or a planet.
Yeah, makes sense.
But in quantum mechanics, spin is, well, it's a bit more abstract than that. It's an intrinsic property of particles. It's just something they have, like mass or charge.
Okay, so it's not that they're actually spinning.
Not in the way we usually think about spinning, no. But they behave as if they have this intrinsic angular momentum. It's kind of like a built-in rotational energy, even when they're not moving through space.
So it's spin in, like, air quotes.
Exactly. And this intrinsic spin has a lot of really important consequences. It affects how particles interact with each other, how they behave in magnetic fields, all sorts of things.
Okay, so it's not just some theoretical quirk. It has real-world implications.
Huge implications. Like,
Yeah.
we wouldn't have things like MRIs or even modern electronics without understanding spin.
Wow. Okay, so where should we go from here? Should we start with electron spin?
Yeah, I think that's a good place to begin. Electron spin is sort of the foundation for understanding spin in general.
All right, let's talk about the electron then. It's this tiny little particle that's buzzing around the atom, right?
Right, and every electron has this intrinsic spin, like we were talking about. But here's the thing. It's not like it can spin in any random direction.
Oh, so it's quantized. Like, it can only have specific values.
Exactly. For electrons, the spin quantum number is always 12, and this means there are only two possible spin states. Spin up, which we usually denote as +12, and spin down, or -12.
Just like a tiny little switch, up or down.
Yeah, that's a good analogy. And this binary nature of electron spin has a ton of consequences. One of the most important is the Pauli exclusion principle.
Okay, I've heard of that. Something about no two electrons being in the same state.
Exactly. The Pauli exclusion principle states that no two electrons in an atom can have the same set of quantum numbers. And since spin is one of those numbers, it means that two electrons in the same orbital have to have opposite spins, one up, one down.
So spin is kind of like a rule keeper. It keeps the electrons from all crashing into each other.
In a way, yeah. It's what gives atoms their structure and stability. Without the Pauli exclusion principle, all the electrons would just pile up in the lowest energy state, and matter as we know, it wouldn't exist.
Okay, so this little up or down spin of the electron is dictating how the whole atom is built. It's kind of mind-blowing.
It really is, and it doesn't stop there. Electron spin also affects how atoms interact with light, with magnetic fields.
Yeah, I remember reading about spin-orbit coupling, where spin interacts with magnetic fields, right?
Right. So when an electron orbits an atom's nucleus, it creates a tiny magnetic field. And that magnetic field interacts with the electron's spin, which is also a magnetic property. This interaction leads to these subtle shifts in the electron's energy levels.
Okay, so the spin and the orbital motion are kind of coupled together.
Exactly. And these shifts in energy levels have a direct impact on the way atoms absorb and emit light. We can actually see these shifts in the spectrum of light that atoms emit or absorb, which is called the fine structure.
So this abstract spin property is leaving its fingerprints on something we can actually measure, the light itself.
Exactly. And by analyzing these spectral lines, we can learn a lot about the structure of atoms and molecules.
This is getting really deep, but it's so cool. We're seeing how this tiny property of the electron, this spin, is affecting how atoms are built, how they interact with light, all sorts of things.
And we're just scratching the surface. Electron spin also plays a crucial role in all sorts of modern technologies.
Okay, let's talk about that. What kind of technologies are we talking about? I've heard about quantum computing, for example. Is that related to spin?
Very much so. In fact, electron spin is one of the most promising candidates for building quantum bits or qubits, the building blocks of quantum computers.
I know everyone is talking about quantum computers, but I still don't really understand what they are or how they work.
It's a complex topic, but I can try to give you a simplified explanation. So in classical computers, the ones we use every day, information is stored in bits, which can be either 0 or 1.
Right, like a switch being on or off.
Exactly. But in a quantum computer, information is stored in qubits, which can be 0, 1, or a superposition of both.
And superposition, what does that even mean?
It means that the qubit can be in both states simultaneously. It's kind of like a coin spinning in the air before it lands. It's not heads or tails until we measure it.
So it's in this weird, undefined state, both 0 and 1 at the same time.
Precisely. And this allows quantum computers to perform calculations in a completely different way than classical computers. They can explore many possibilities at once, which gives them the potential to solve certain types of problems much faster.
Like what kind of problems?
Well, one example is breaking encryption codes that are currently considered unbreakable by classical computers.
Oh, wow. So quantum computers could revolutionize cybersecurity.
Absolutely. They could also have a huge impact on fields like drug discovery, materials science, and artificial intelligence.
And all of this because of the weird quantum properties of spin.
Yeah, it's amazing how this seemingly abstract property could have such a huge impact on our lives.
So we've been talking about individual electrons and their spin, but I know there's also something called atomic spin, right?
Right. Atomic spin is basically the total angular momentum of an atom.
Okay, so instead of just one electron, we're now looking at the whole atom.
Exactly. And to understand atomic spin, we have to consider not just the spin of the individual electrons, but also their orbital angular momentum.
Orbital angular momentum, what's that?
Well, just like the Earth orbits around the sun, electrons orbit around the nucleus of an atom, and this orbital motion also contributes to the atom's overall angular momentum.
So it's like the spin of the electron plus the angular momentum from its orbit.
Plus, we also have to consider the spin of the nucleus itself, which can also contribute to the total atomic spin.
Wow, so it gets even more complicated when we zoom out to the whole atom.
It does. But the good news is that for many purposes, we can simplify things a bit. In many cases, the spin of the nucleus is much smaller than the other contributions, so we can often ignore it.
Okay, so the main players are the electron spin and the orbital angular momentum.
Exactly. And these two can combine in different ways to give the atom a net angular momentum, which we call the atomic spin.
And just like electron spin, this atomic spin has real-world implications, right?
Absolutely. Atomic spin is the basis for a lot of important technologies like nuclear magnetic resonance or NMR.
NMR, as in MRI.
Exactly. MRI, or magnetic resonance imaging, is basically a medical application of NMR. It uses strong magnetic fields and radio waves to manipulate the spin of atomic nuclei, usually hydrogen nuclei in the case of medical imaging. And by detecting the signals from these spinning nuclei, we can create detailed images of the inside of the body.
So every time someone gets an MRI, they're actually experiencing the effects of atomic spin firsthand.
Exactly. And it's not just medical imaging. NMR is also a powerful tool for chemists and physicists. It allows them to study the structure and dynamics of molecules at the atomic level.
Okay, so atomic spin is essential for understanding and manipulating matter at a really fundamental level.
And it also plays a crucial role in some very precise technologies, like atomic clocks, for example.
Atomic clocks, how are they related to spin?
Atomic clocks are based on the very precise frequency of light that atoms emit or absorb when they transition between different energy levels. And these energy levels are very sensitive to the atom's spin state.
So by carefully measuring these transitions, we can create incredibly accurate clocks.
Precisely. Atomic clocks are so accurate that they lose less than a second every 100 million years.
Wow, that's more precise than anything I could ever imagine needing. What do we even use such accurate clocks for?
They're used for all sorts of things, from GPS navigation to synchronizing telecommunications networks. Without atomic clocks, our modern world would basically grind to a halt.
So this fundamental property of atoms, their spin, is literally keeping our world running on time.
In a way, yeah. It's one of those things that's so fundamental that we often take it for granted. But it really is crucial for our modern way of life.
Okay, so we've talked about electron spin, atomic spin, and some of the amazing technologies that they underpin. But I know there's a lot more to this story. Like, how do we actually describe spin mathematically? It can't just be arrows pointing up or down, right?
Right. Mathematically, spin is described using something called spin operators.
Operators.
Like,
Mathematical instructions.
in a way, yeah. Spin operators are mathematical objects that act on quantum states to describe the spin of a particle.
And these operators capture the weird quantum nature of spin.
Exactly. One of the key things about spin operators is that they don't commute.
Don't commute. What does that mean?
It means that the order in which you apply them matters. If you apply operator A and then operator B, it's not the same as applying operator B and then operator A.
Okay, so it's not like regular multiplication where the order doesn't matter.
Right. And this non-commutativity is a direct consequence of the Heisenberg uncertainty principle.
I've heard of that. Something about not being able to know both the position and momentum of a particle at the same time.
Exactly. The uncertainty principle applies to spin as well. It means that we can't know both the direction and the magnitude of a particle's spin at the same time.
Okay, so there's always some inherent fuzziness when it comes to measuring spin.
Precisely. And this fuzziness is what makes quantum mechanics so different from classical mechanics.
Okay, I think I'm starting to get a glimpse of the mathematical weirdness that underlies this whole spin thing.
And believe me, we're just scratching the surface here. There's a whole lot more to it.
I bet. But maybe we should move on to something a bit more concrete. Like, what are some of the key experiments that have helped us understand spin?
Well, one of the most famous is the Stern-Gerlach experiment.
Okay, I've heard of that name before.
Yeah.
But I'm not sure I remember what it was about.
The Stern-Gerlach experiment was conducted back in 1922, and it provided the first direct evidence for the quantization of spin.
Quantization, meaning that spin can only have discrete values.
Exactly. So in the experiment, they sent a beam of silver atoms through a non-uniform magnetic field.
Okay, and what happened?
Well, classically, you would expect the beam to spread out continuously as it passed through the field. But that's not what happened.
Oh, so something quantum happened.
Yeah. The beam split into two distinct beams, corresponding to the two possible spin states of the silver atoms.
So it was like the atoms were being sorted by their spin.
Precisely. And this was a huge surprise at the time. It showed that spin is a real, measurable property, and that it's quantized.
That must have been a game changer for the world of physics.
It absolutely was. It was one of the key experiments that led to the development of quantum mechanics as we know it today.
Wow. Okay, so we've talked about the theory, we've talked about the experiments, we've talked about some of the applications. Is there anything else we should cover before we wrap up?
Well, we could talk about some of the more cutting-edge applications of spin, like spintronics.
Spintronics, as in using spin to create new electronic devices.
Exactly. Spintronics is a rapidly growing field that aims to exploit the spin of electrons to create new types of transistors, memory devices, and even logic gates.
And this is different from traditional electronics because it's not just about the flow of charge, but also about the spin of the electrons.
Right. In traditional electronics, we use the charge of the electron to carry information. But in spintronics, we can use the spin as well. And this gives us a lot more flexibility and potential for creating new and exciting devices.
What kind of devices are we talking about?
Well, one example is MRAM, or magnetic random access memory. MRAM uses the spin of electrons to store information, and it has the potential to be much faster and more energy efficient than traditional RAM.
So our computers could become even faster and more powerful thanks to spintronics.
Absolutely, and that's just one example. There are many other potential applications of spintronics being explored, including spin-based transistors, logic gates, and even quantum computers.
So spin is not just a theoretical curiosity. It's a powerful tool that has the potential to revolutionize the way we live and work.
It really is, and it's just one example of how the weirdness of the quantum world can lead to amazing technological advances.
Wow. Well, I think we've covered a lot of ground today. And I have to say, my brain is feeling a bit full, but in a good way.
Mine too. It's always exciting to talk about this stuff.
So to wrap things up, what would you say are the key takeaways for our listeners?
I'd say the most important thing to remember is that spin is a fundamental property of particles. It's not that they're actually spinning, but they behave as if they have this intrinsic angular momentum.
And this spin has huge consequences for the way the universe works, from the structure of atoms to the behavior of black holes.
Exactly. It's behind a lot of the technologies we rely on every day, and it has the potential to lead to even more amazing advances in the future.
So next time you hear the word spin, remember that it's not just about something physically rotating. It's a glimpse into the strange and wonderful world of quantum mechanics.
And it's a reminder that the universe is full of mysteries waiting to be uncovered.
That's a great note to end on. Thank you so much for joining us on the Deep Dive today.
It was my pleasure. Thanks for having me.
And for our listeners, keep exploring, keep asking questions, and keep diving deep into the fascinating world around us. Until next time.